Okay, so I believe it's time to start. Good afternoon, everyone. My name is Ugo Simeoni. I'm Research and Innovation Manager at the European Turbine Network. Welcome to the third episode of the Flexible Power Generation webinar series organized by the European Turbine Network in cooperation with the ETIPSNet, European Technology and Innovation Platform Smart Networks for Energy Transitions, and 5 Horizon 2020 projects, namely the Flex and Comfu, HYFLEXPOWER, Pump Heat, SO2 Flex, and Turbo Reflex. I'm very delighted to see the high interest from a large audience on the role that flexible power generation can play in achieving the EU's climate goals and in supporting the decarbonization. But before I carry on with my introduction, I would like to introduce you today's speakers. So Mr. Ertan Ilmaz from Siemens Energy, Ms. Marie Perrine Dureau from Engie Solutions, Mr. Steven Stoffer from Smurfit Kappa, Mr. Ian Amos from Siemens Industrial Turbomachinery, and Mr. Sotirios Karellas from National Technical University of Athens. All the speakers today are part of the Horizon 2020 project HYFLEXPOWER, which stands for Hydrogen as a Flexible Energy Storage for a Fully Renewable European Power System. While in the first episode we have analyzed the strategies on hydrogen and system integration, during today's episode we will explore how the HYFLEXPOWER solution can contribute to this strategy. And indeed, the aim of the project is to demonstrate that renewable hydrogen, which can be generated by the excess of electricity from renewable energy sources, can serve as a flexible means of storing energy, which can then be used to power an industrial gas turbine during high demand. And it has been estimated by the project partners that by burning hydrogen in the gas turbine, there would be a saving up of 65,000 tons of CO2 per year for an SGT 400 gas turbine. Now, further details will be definitely given by the speakers during the presentation. So without any further ado, I would like to leave the stage to our first speaker, Mr. Ertan Ilmaz, who is the project coordinator and H2 portfolio manager at Siemens Energy. Siemens' role in the project is to supply the hydrogen production and develop the hydrogen gas turbine. Ertan, could you give us a general introduction to the project, please?
Yes. Good afternoon, everybody. Thank you, Ugo, for the introduction. I'm Ertan Yilmaz and delighted for having this opportunity to talk to you about our HYFLEXPOWER project. I'm the hydrogen portfolio manager at Siemens Energy's generation division and at the same time the project coordinator for HYFLEXPOWER. In my talk today, I will give you a brief overview of the project, the consortium, key milestones and expected results. If you go to the next slide, please. HYFLEXPOWER is a brownfield power to hydrogen to power application to an existing combined heat and power plant in Saillat-sur-Vienne, France. The project's main goal is to demonstrate of the decarbonization of the power plant by utilizing excess renewable energy to generate and store hydrogen on site and then to convert it back to electricity and heat at a later date. Once executed, this project will be the world's first demonstration of a fully integrated industrial scale power to hydrogen to power path for a CO2-free power generation with an advanced high hydrogen gas turbine. The Siemens Energy-led consortium has an overall volume of about 15.2 million euros. A significant portion of the funding, approximately 70%, has been funded by the European Union's Horizon 2020 Research and Innovation Program. The project has started in May 2020 and will continue for 4 years until April 30, 2024. Our consortium partners are shown here and include a mixture of European industrial partners, research institutes, and universities. More details on the project concept, on the consortium partners' responsibilities are shown in the next slide. So the HYFLEXPOWER project will develop and demonstrate an advanced plant concept that will modernize and improve the existing combined heat and power plant. Here on the left is a schematic of the project concept. The current setup is shown in the bottom of the schematic. The plant is operated during the winter months only and uses natural gas to generate electricity via a Siemens SGT-400 turbine and a recovery boiler to produce steam. The top of the schematic shows the plant's site upgrade to utilize excess renewable energy for generation, storage, and supply of hydrogen for re-electrification. It includes an electrolyzer, compressor, storage tanks, and a natural gas and hydrogen mixing station. Now to the consortium partners' responsibilities. Siemens Energy is the coordinator and responsible to supply the PEM electrolyzer system for hydrogen production and to develop and upgrade the existing SGT-400 gas turbine with high hydrogen capability with up to 100% H2. Engie Solutions is the operator of the plant and will build the hydrogen production, storage, supply facility, including the hydrogen compressor, storage tanks, and the natural gas hydrogen mixing station. Centrax, the gas turbine packager of the SGT-400, will upgrade the gas turbine, generate a package for hydrogen operation, and install the upgraded demonstrator gas turbines on site for this demonstration runs. The German Aerospace Center, the University College London, the University of Duisburg-Essen, and the Lund University all support the dry low emissions high hydrogen gas turbine technology development for the SGT-400. And the National University of Athens will perform economic, environmental, and social assessments for business case evaluation, carbon footprint, and policy recommendations. And least but not last, Arctic supports the consortium in operational project management and in the communication and dissemination activities. The next slide provides an overview of the key milestones, the expected results, and their impacts. The aerial picture shows the current industrial pilot demonstration site at Saillat-sur-Vienne, where the HYFLEXPOWER project will be built. In the front is the cogeneration plant with the Siemens SGT-400 gas turbine, and at the background, the Smurfit-Kappa's recycled paper manufacturing plant. Currently, the consortium is making good progress with the design of this advanced plant concept, and the first milestone will be reached by the end of 2021, when the hydrogen production, storage, and supply facility will be installed. In 2022, the upgraded demonstrator gas turbine will be installed, and the new components at site will be commissioned. The second important milestone will then be reached in the fall of 2022, when the advanced plant concept will be demonstrated with natural gas hydrogen mixtures of higher than 10% of hydrogen. The main milestone and the ultimate goal of the demo is to demonstrate in the fall of 2023 the advanced plant concept up to 100% hydrogen for CO2-free energy production from stored excess renewable energy. So, with all of this, the expected results and their impacts of the HYFLEXPOWER project are as follows. When completed in 2024, HYFLEXPOWER will be the world's first demonstration of an industrial scale power to hydrogen power solution with an advanced hydrogen turbine. This will have further implication on three additional important aspects. First, it will demonstrate the importance of hydrogen as a long-term energy storage technology on a high renewable grid. Second, it will also demonstrate the decoupling of renewable energy generation from electricity demand, and therefore it will enable the renewable energy sector for additional revenue streams. And third, it will show the potential for future utilization of existing assets to produce green energy and heat through gas turbine and plant upgrades. It will also validate the newly developed SGT-400 dry low emissions technology, high hydrogen technology up to 100% hydrogen. Of course, these results will further include the economic, environmental, and social assessments for business case evaluation, carbon footprint, and policy recommendations. With this, I would like to conclude my presentation and hand over back to Ugo. Thank you very much for your attention.
Thank you very much, Ertan. This was very effective, and we are I would like to see if there is any questions. You can write in the chat box. Any clarification question? And anyway, we are planning to have a short round of questions towards the end of this webinar. So we have a question from which is the size of the storage?
Yeah, we will have the size of the storage will enable us to operate at really full load conditions for a little more than an hour with our SGT 400 gas turbine once complete.
Okay.
Of course.
Okay, thank you. Okay, another question. Are we primarily planning to use both wind or solar power for electrolysis, or will there be a preference?
It probably will be primarily wind power, but the details will be once we are ready in 2022, depending on the situation and the electricity supply, that will be details will be finalized then. For that, Engie will do an analysis and we will then go from there. But at this point of time, it seems to be that wind will be the primary source.
Okay, thank you. And then the last one is a clarification question. If the SGT 400 will be revamped.
Can you repeat that quickly?
If the SGT 400 will be revamped.
Revamped? Can you? I'm sorry to ask this question again. Revamped?
If it will be upgraded.
Oh yeah, certainly yes. To operate up to 100% hydrogen, yes, it will be retrofitted with new burners. Between now and in 2023, we are having a significant effort to develop technology to be capable of operating up to 100% hydrogen in DLE mode. Of course, we will supply with a retrofit engine, and we will build it in and then operate with the revamped SGT 400.
Okay, then thanks a lot, Ertan. I see other questions, but I would like to move on to the next presentation, and then if we have enough time towards the end, we will answer those questions. Otherwise, we will email the questions to the presenter. So I would like now to move to the next speaker, Ms. Marie Perrin-Dureau, Innovation and Green Industry Director at Engie Solutions. Marie,
hello.
Give us more details on the Engie's hydrogen strategy. Thank you.
Yes, good morning, everyone. So next slide, please. Thank you for being here. So as you may know, Engie is a worldwide leader in energy transition, and our purpose is to accelerate the transition to a carbon neutral economy. We have 4 main businesses: natural gas production, natural gas networks, renewable energy productions, and client solution. Client solutions means energy services for B2B clients, being public authorities or private companies. And this is Engie solution means energy services. Next slide, please. So Engie Solutions for Industry represent 20,000 employees and 3.8 billion of revenues. And we have 3 main purposes for our clients. The first is providing low carbon resources and energies, then to optimize energy consumption, and third, to deliver Industry 4.0 solutions. Therefore, hydrogen is a full component of this strategy. Next slide, please. And in particular, green hydrogen, which is, in our view, a very powerful instrument to decarbonize the industry. And as you know, green hydrogen especially when it is directly connected to renewable electricity, has no impact on greenhouse gas emissions, while each kilogram of grey hydrogen would produce 10 kilograms of CO2 equivalent. This is why Engie has been and is still a world pioneer in green hydrogen. And for example, we've been a founding member of the Hydrogen Council that is structuring the value chain and all the players in this field. Next slide, please. So our vision is to encourage the development of hydrogen for diverse final usage, in particular grid services and like storage of renewables electricity during peak productions, but also off-grid services and, for example, providing energy in remote locations, and final usage for industry, mobility, and buildings. Next slide, please. To materialize this vision, we have developed turnkey offers that aim at providing green hydrogen to our clients. For example, we are able to design, invest in, build, operate, and maintain renewable H2 plants that aim at providing green hydrogen to our industrial client at a specified quantity and quality. And similarly, we have developed a turnkey offer, a global offer, on refueling station for hydrogen mobility. And combining these two, industry and mobility, we are actively taking part in the development of hydrogen territorial hubs in various parts of France and as well as other European countries. Next slide, please. So this is a snapshot of some of large industrial scale projects all over the world. So a mix of mobility and industry uses. And next slide. This is a focus on France, where you can see we have already a mix of mobility and industry references in green hydrogen. And this concept of territorial hubs that are popping up on different parts of the map. And then southwest of France, you will find the city of Saillat-sur-Vienne, where you will find the demonstrator of the HYFLEXPOWER. So beyond this project, I would say mature project for mobility and industrial use, Engie is investigating a number of innovation projects to prepare for the future of hydrogen. And in this regard, HYFLEXPOWER is a key project in our roadmap for industry. It allows us to explore technical solutions using hydrogen as a vector to replace or act in combination with natural gas for combined heat and power production at an industrial facility. Alongside this project, we are also working on testing the substitution of natural gas by hydrogen in high temperature furnaces like glass, for example, in our semi-industrial facility near Paris, in our R&D department. And we are also looking at liquefaction technology for future mobility uses like in the marine sector, for example. Next and the last slide. So as I said, HYFLEXPOWER is a key component of our roadmap for hydrogen for industrial uses. The project is located at Smurfit Kappa's site, which is a long-term partner of Engie Solutions, as we are responsible for operating the site's power plant. In the project, as it was said by Siemens, we are responsible for installing the full hydrogen value chain up to the natural gas and hydrogen mixture for injection into the turbine. The engineering will be carried out by our engineering subsidiary ERAS, and also with our R&D department. And then the commissioning and the test will be carried out in 2022 and 2023. So this is it. And as you say, as you see, HYFLEXPOWER is really a key project in our hydrogen roadmap, and we look forward to the results of this important project.
Thanks a lot, Marie. Is there any question? Okay, so what will be the flexibility on using fuel gas or hydrogen?
So as it indicated, the test will be run in 2 phases, and the first test will be carried out in April 2022 with 30% hydrogen mixed with natural gas. And the second phase of the test will be the year after, April 2023, and it will be up to 100% of hydrogen.
So the 30% will be in volume?
That's a good question. Yeah,
maybe I can answer that.
Yes.
Give it to you, Marie.
Yes, of course.
Yeah. Yes, it will be by volume, and the gas turbine capability will be, anywhere between pure natural gas and our target is in the first phase to reach this 30% hydrogen capability. Yeah, but at the ultimate goal in this first testing campaign is really to operate the advanced plant concept and push the hydrogen limit as high as possible. Yeah.
Okay, thank you. Then another quick question. Okay, the type of turbine is an SGT 400, which I'm not sure if this is for Marie, which is the gas turbine load target compared to natural gas base load for 100% hydrogen operation. Perhaps this question will be answered later on during the presentation of Ian.
Yes, I can cover that.
Yeah, okay. So I would suggest to move on to the third speaker. Thanks, Marie. And I will take note of the other questions. And so we have with us Stephen Stouffer, Group Vice President, Sustainable Development at SmartFit Kappa. SmartFit Kappa is a leading provider of paper-based packaging in the world. So Stephen is going to give us an end user's perspective on the sustainable use of energy. Stephen, the floor is yours.
Thank you, Ugo, and good afternoon. Thank you for all who is taking the time to be with us this afternoon. I will give a very short introduction of our company, why we are interested in this project, and the questions that we have that we would like to get answered in this project. Maybe just a few more words about SmartFit Kappa. As Ugo said, we are one of the largest global suppliers of paper-based corrugated packaging solutions. We have 65,000 customers, of which 60 to 70% ends up with FMCG companies such as Nestlé, Unilever, Mondelez, and Procter & Gamble. And the pandemic has shown how essential our type of packaging is for society. Without our packaging, many vital supply chains, such as medical equipment, pharmaceutical, food and sanitation products, could not continue to be delivered, especially in the first wave of the pandemic. We are almost 100% paper-based in our products, and paper is of all packaging materials the most sustainable. Next, please. Our approach Next slide, please. Our approach to being sustainable is based on the three classic pillars: people, planet, and business approach, business, impactful business. And we have an approach to the Sustainable Development Goals of the United Nations. And we have defined a number of the SDGs that we can impact. SDG 13, climate action, is one of those because as a paper producer, we are an energy intensive industry and as such a large emitter of CO2. Next, please. Our circular business model is really circular. Our packaging solutions are made from renewable, recyclable, and biodegradable material, and 85% of the products that we put out on the market is actually recycled, which is a very high percentage. We are, in our sustainability approach, we are working to take the linear elements out of the system. And as you can imagine, the use of fossil energy is one of those elements. Next, please. Of course, we have ambitious goals because setting ambitious goals helps us to keep focus, and it helps us to keep focus on the issues with high priority. And as you can imagine, one of the most important goals that we have is to contribute to climate change. Again, SDG number 13. And our current achievement is we have decreased our carbon intensity since 2005 until the end of 2019 by almost 1/3, and we are counting. So we have increased our target for 2030 to 55%, and we have also recently announced that we will be net zero by the end of 2050, which is very important to, as I said again, to keep us focused. Next, please. So slowly coming to the subject of today, that we have three pathways to lower our fossil CO2 emissions. The first one is efficient energy generation, and we do that by investing in highly efficient CHP systems and by improving the efficiency of our existing boilers. The second way to do that is to use efficient energy, and we do that by investing in technologies that reduce the energy consumption or by re-engineering our processes and implementing smart energy efficient solutions. And then thirdly, the switch to renewable energy. Where possible, we use CO2 neutral biofuels and other renewable solutions. So that brings us to the question, where does hydrogen fit in for Smurfit Kappa? Well, 80% and more, so about 80%, a little bit over 80% of our fossil emissions occurs in our paper mills. We have two types of mills. We have kraftliner mills, where on the basis of wood, paper is produced. These mills are basically zero fossil CO2. They are CO2 neutral almost. Our challenge is in the recycled paper mills. Those are the mills where we produce paper from recovered fibers. These depend very much on fossil fuels. And we can do a lot by efficient energy generation and efficient usage, but not enough to reach the net zero. So that's where the non-fossil alternatives come into place, but all of these have issues. For example, the biomass has an issue of availability. The geothermal is not everywhere possible, and green electricity has issues with the grid capacity, connectivity, and of course availability. So that raises the question, how can hydrogen help for us? Next, please. Well, as a starter, maybe to manage your expectations, but if we can use green electricity direct, that is preferred for us over the use of hydrogen. We should only use green hydrogen when green electricity options are exhausted. And it occurs that in the current state of affairs of hydrogen, for the paper industry, hydrogen applications seem limited. It is not the most efficient application for the low temperatures heat. That means between 150 and 200 degrees Celsius. as they are used in our industry. And the green electricity is much preferred as it eliminates the conversion losses from electricity to hydrogen. Next, please. Let me compare the hydrogen production on-site or off-site together. So via CHP, we would do that on-site, or via a power plant, the grid. And there, of course, there is this, if we take the hydrogen from the grid, the efficiency of the electrolysis is 70%. So that is already a first indication that only excess green electricity should be used to produce hydrogen if possible. If we then convert the hydrogen at the power plant, that has an efficiency of 45%, because the 70% times the 65% efficiency at the power plant gives us 45 efficiency, where if we do that on site with a CHP, we have a efficiency of 60%. And I think it is very illustrative to say that if we would use 1 hour of efficient on-site hydrogen conversion at a medium-sized paper mill, which Saillat is, and we do that into electricity, that saves the annual electricity use of 8 households compared to the conversion at the power plant. So that's just 1 hour of efficient use of hydrogen. Next, please. That brings me to my last slide, and that is that there are, of course, many questions still unanswered for the use of hydrogen for us. And this is why we are also so much interested to participate in the project. One of the questions is the conversion cost of turbines and boilers. Is there extra maintenance needed? There are higher NOx emissions, and will that impact electricity production? And there are more. So these are all unanswered, and we hope to answer these during the project. And then, of course, as a very last one, are there additional barriers for use on-site hydrogen in the area of safety? With that, I would like to thank you for your attention and conclude my presentation.
Thanks a lot, Stephen. As usual, I would like to invite people to write questions in the chat. Okay, there is one question which is whether the plant is working 24/7.
Yes.
And I think this is more like strategic question, whether, because what doing this pilot in France where electricity from the grid is with relatively low greenhouse gas emission intensity?
I'm not sure. I wasn't close to the setup of the project, but I could imagine that that is because the partners were interested to do it in this place. It's probably a coincidence. Yeah. It happened there.
Maybe, Steven, maybe I can interrupt on that. The plant in France is only operating in the winter time. So that means that during summer we have the possibility to do tests, because if the plant is running 24 hours per day, 7 days per week all year, it's of course very difficult to do a test there. So it's that's one of the reasons. Mm-hmm.
Okay, thanks a lot. Thanks, Theo. I believe there are no further questions. So I thank you again, Stephen. And I would like to move on to the next speaker, Ian Amos, product family owner at Siemens Industrial Turbo Machinery. Ian, the floor is yours.
Thank you, Ugo, and good afternoon. So, Ian Amos, product family owner at Siemens Energy, based in Lincoln, UK, where I work with the small industrial gas turbine portfolio. So I'm going to spend a few minutes talking about the changes required on the gas turbine power systems in order to allow it to be fueled by hydrogen-rich fuels. So next slide, please. So first of all, hydrogen is not a completely new fuel for gas turbines, and there is a history of burning waste refinery gases and other off gases which are rich in hydrogen, and we've done that for a number of decades now. However, the hydrogen-rich fuels were mainly restricted to diffusion flame combustion technology, which is associated with high levels of nitrogen oxide generation. There are some technologies such as water injection, which are used to reduce the reaction temperatures and drop the NOx production. But the key technology gap that exists at the moment is the ability to burn up to 100% hydrogen in gas turbines using dry low emissions combustion technology. So that directly controls both the nitrogen oxides and the carbon monoxide generation in the combustion directly. So the capabilities of some of the dry low emissions combustion systems, is already quite impressive. We have seen up to 60% hydrogen by volume, but there is a gap between 60% and 100%, and that does require a step change in technology. And as stated on this slide on the top right, even at the current levels, there may be a need to change some specific hardware in the turbines at these sort of levels, and also there may be some operating restrictions. There was a question asked about what power we intend to operate these engines, and the intention is to be able to operate at 100% load, i.e. the same load on full 100% hydrogen fuel as we do for the natural gas fuel. So what is difficult about it? So move over to the next slide, please. The difficulty really is all to do with the properties of hydrogen. So hydrogen has 3 times the energy per kilogram that natural gas has, but it is the lightest element in the periodic table, about 1/8 of the density of methane, and due to the lightness it diffuses readily, and so poses challenges on pipe materials, fittings, and other components. It can escape easier through gaps which are impervious to natural gas. On the combustion kinetic side, it has a flame speed up to 6 times or so higher than methane, and that forces the flame to stabilize much closer to the burner tips and gives increased surface temperatures, which needs to be accommodated for. One particular feature is flashback, which where the flame speed is higher than the incoming fresh gas supply, which means the flame can propagate back in the burner, burn where it shouldn't burn, and cause significant damage. So resistance to flashback is a very strong design criteria, and also a practical constraint when using current technologies. So as hydrogen is carbon free, the CO2 emissions drop with increasing hydrogen content, as you can see on the graph. The relationship is very nonlinear. So for example, at 60% hydrogen by volume, there is only a 30% reduction in the CO2. So for big decarbonisation, we need to have higher hydrogen concentrations. You're talking 80, 90, 100%. And as you can see from the graph, that is really in the technically challenging area where the properties start to change very rapidly with hydrogen concentration. Okay, next slide, please. So the level of modification is very dependent on the level of hydrogen in the fuel, and changes are driven by safety topics, by emissions characteristics, and sort of general combustion stability issues. These changes are highly engine specific, So this chart really just provides a qualitative overview. In general, 10% of hydrogen can be comfortably accommodated with the existing setups without the need for any major modification. Up to 30%, we do expect some changes, minor changes on burners, auxiliaries and controls. Some engine frames are already capable of providing up to that sort of level, but you have to recognise from about 25% hydrogen upwards, the package will usually need to be recertified. Pipe work and valves may require material changes to upgrade it to, for example, stainless steel, and there will be modifications to things like gas detection equipment and controls. When you move from 50% and up, the anticipation is there are more modifications in the burner. We are looking, as part of this programme, at new burner designs. There are modifications to the fuel system, and that's really as much to handle the larger volumetric flow of the fuel as anything else. And there are probably some operational requirements that need to be considered. Can you start up on high hydrogen gas, or will you on either conventional natural gas or a much lower concentration? In general, it should be stated that performance may also need to be adapted to accommodate the high levels of fuels. And as I stated before, the intention of this programme is to achieve the same level of power as we do on natural gas. Next slide, please. And really, this is, in summary, any conversion of an existing installation to high hydrogen 2, such as the Saillat site, requires a full audit to understand what is the current capabilities and limitations of the components in the plant. For the main turbine generator systems, the key features requiring modification are identified, and on the HYFLEXPOWER, Siemens Energy will be closely coordinating activity with Centrax, who have responsibility for the package modifications, and Siemens Energy will be focusing on the modifications required in the gas turbine core, and particularly the combustion. So we are at the moment in relatively early stages of the project. We're developing the basic combustion technology, and that's aided by extensive rig testing, and providing definitions of the various performance parameters to the other partners in the programme for design of the rest of the installation and also the evaluations. So we're looking forward to this programme continuing and being able to update you on further developments in the future. So thank you very much for your attention.
Thanks a lot, Ian. I would like to check whether there are questions. Yes, some questions are on the fleet, whether the A65 and A45 fabrication was stopped or it's still ongoing.
Well, we've shown there on the first chart, yes, that there is capability of those products with hydrogen at the moment, predominantly using water injection to control the emissions. So yeah, we intend to develop a hydrogen capability across the whole of the fleet, and certainly the work that we're doing on HYFLEXPOWER, it's not going to be restricted to the SGT 400. We'll be using that technology and rolling it out across the whole portfolio.
Okay, thank you. And I think other questions similar were answered during your presentation, but what is another one I would like you to answer is, what is the current TRL level of your 100% hydrogen turbine, and what will be the TRL target at the end of the project?
The technology readiness level, I don't know, Ertin, are you closer to those definitions?
Its TRL7 is demonstrated.
Yeah, the end of the project, it will be TRL7 demonstration on a engine on the plant, and currently we are developing our technology for dry low emissions technology with the ultimate goal really to have it ready for implementation by 2023 for the summer campaign of 2023. Okay.
Thank you. And do you see impact from materials and maintenance when running 100% hydrogen?
I mean, there are expected changes that we need to do material. I already mentioned that, you know, outside the turbine, we would have to use stainless steel more extensively, probably change the valve body materials. So yes, that is anticipated. The intent is to use materials so we can maintain the same maintenance schedule as we currently have on the product.
Okay, and hydrogen and natural gas will be mixed inside the fuel gas skid or upstream?
No, that will be mixed upstream. So the skid edge will be supplied the mixed out fuel. So that will be a variable blend between 0 and 100% hydrogen.
Okay. So the last question I take, and then we move on to the next presentation, is would you expect that turbines in the future will be fuel flexible or rather hydrogen only?
We expect them to be fuel flexible. So as I said, anything between 0% hydrogen, i.e. 100% natural gas and 100% hydrogen.
Okay. Thanks a lot, Ian. Unfortunately, we don't have enough time to answer all the questions. So I would move on to the next presentation. The next presentation, we have Mr. Sotirios Karellas, professor at National Technical University of Athens, who will give us some insights on the environmental assessment of power to hydrogen to power technology. Sotirios, the floor is yours.
Thank you very much. Thank you very much for the invitation. And this is, I have to congratulate for the excellent organization of this seminar. So I am Professor Sotirios Karellas. I am a professor at the National Technical University of Athens, and our laboratory is the so-called Laboratory of Steam Boilers and Thermal Plants, which is a laboratory that has a lot of experience in thermochemical processes, power plants, but also environmental issues. We have high collaborations in these fields with other universities, but also with important industrial partners. And a budget of more than 5 million euros in the last 10 years. So we have bilateral collaborations also with Greek and international technology developers. We have the industrial partners. And the case of HYFLEXPOWER is a very important case for us. We are involved in this project in order to model and optimize the cycle of the HYFLEXPOWER technology. We will assess techno-economic analysis, and one of the most important issues that we will have to face is the environmental assessment, as well as the socio-economics of the process. But let's have a look on hydrogen. Since we are discussing, my presentation is focusing on the environmental issues. Let's see why hydrogen. Hydrogen today is a key fuel. It is discussed a lot. It's a hot topic nowadays in the energy production due to its characteristic of storing energy. And here we can see the first phase in the European hydrogen strategy, which is to have around 6 gigawatt electrical electrolyzers until 2024. And then we are proceeding with a high amount of electrolyzers installed. The milestones are to have a competitive green hydrogen and to open the European market regarding the H2, the trade market. And finally, in 2030 to 2050, 1/3 of electricity generation is used for hydrogen production. So we will, the milestone of the European Union is to have hydrogen in all sectors and to have a full maturity and development of market and technologies. So hydrogen, when combusted, as we know, leads to zero emissions in all systems. We have the possibility, now we are discussing about the coal phase down, so hydrogen is a fuel that allows us to use wasted energy and to curtail the surplus of energy. So here are the important parts, the important stages of the hydrogen to power technologies, power to hydrogen to power technologies. So first of all, the production of hydrogen, dealing with the electrolysis, and it was also discussed a little bit before, using renewable energy. So we have then the hydrogen storage, and we have the hydrogen re-electrification. Why am I describing this? Because, as I will say afterwards, we need to go from the beginning on in terms of environmental analysis, and not only to the emission, so to the end emission. So we need to go in a technology according to life cycle assessment, according to the life cycle approach. We need to go from the beginning on up to the end of life of the product. So the scales, you can see the scales here. We are discussing about large-scale power to hydrogen to power. In this case, as is the case of the project, we are discussing about combined cycle gas turbines or use in boilers and heat recovery boilers. We are discussing about medium-scale power to hydrogen to power, where we speak about fuel cells, smaller gas turbines, etc. And then we have the power to hydrogen small scale, so where we can have the use in fuel cells or other hydrogen or in the residential sector. I would like now to point out the 4 categories of hydrogen. They were said more or less, but I would like to point them out in order to make clear that in this project our aim, as Marie said before, is the use of green hydrogen. So we have the various types, let's say, the various colors, I would say, of hydrogen, the gray, blue, turquoise, and green hydrogen. So as you can see here, the TRLs, and we see here the direct emissions. The direct emission gray hydrogen are quite high. It was mentioned before from Marie. So our project is really aiming at the zero direct emissions going through the electrolysis, and this is a carbon-free technology in terms of emissions in the power plant. So in our project, as it was said also before, we have the first stage, which is the power to hydrogen part, which you can see here, from the renewable energy sources, and it was also said before, from mainly from the wind turbines, but also from the whole, also we are thinking of other renewable energy sources, of course. We are producing the hydrogen, which is being compressed, stored, and then is being combusted in the gas turbine that was mentioned before, producing electricity and heating. So this is also very important because we are discussing about cogeneration, not only electricity generation. So there is also a very important issue dealing with the covering of the heat demands. So our aim is then to reduce the natural gas portion and then to eliminate it. So I end up my presentation here. I would like to say that if we only assess the foreground emissions, we fail to see the largest part of emissions that occur during the entire life cycle of the technology. So that means that we need to have a look not only on the top of this iceberg, but also on the entire life cycle of the technology. And we have to see from component, construction, transport, supply chain configurations, and end of life. For example, dismounting, recycling, waste, reuse, disposal. So all these issues that are parts of this of the circular economy we're discussing today, and that are combined with each technology nowadays, are very important to be discussed in this project. And this is the role of the National Technical University of Athens, because we need to see all these components, how they are linked with their life cycle, how they are linked environmentally with their life cycle. And here that's the case. We have our project, we will have a reference, and our issue, we will have a reference case, and we need to see how better we are in terms of environmental performance as the reference case. As an example, if we have 30% of hydrogen in a combined cycle gas turbine, that means that we have 10% reduction of direct emissions in terms of grams of CO2 to kilowatt hour electric basis. But what about the carbon footprint of the electricity produced? So that is the question that we are asked to answer in this project, and that we are very happy to be in this project. We are very happy to discuss these issues with all the partners and then with all the energy community. I thank you very much for your attention.
Thanks a lot, Sotirios. We do have already some questions in the chat. The first one is, what is the rated size of the electrolyzer? You know, otherwise I think also...
this is a question at the moment that maybe Siemens could answer. So I think that this question is for Siemens.
Yeah.
Ertan?
Yes, can you hear me?
Yeah.
Yeah, the electrolyzer will be utilized to generate hydrogen, to store up to 1 ton of hydrogen and supply it to the gas turbine at the needed time. At this point of time, the size of it, it's going to be on the order of 1.25 megawatt, and the details of it we will be providing at a later stage, preferentially during a demonstration in the year of 2022.
Okay, thank you. Which compression technologies will be used in the process, and what are the proposed pressures for storage?
The pressure is going to be 200 bars, and it's going to be stored in racks with a maximum of 999 kilograms, because we need to stay below 1,000 kilograms of stored hydrogen to comply with the French regulation.
Okay, and this I think is linked also to another question which was done before, and I see also in the chat now if the H2 storage is compressed or liquefied. And here
it's compressed, yes, compressed.
And also, what is the footprint? I'm not sure if you already estimated this.
What is meant by footprint? You mean the size?
I think they mean the size, Marie. Yes, the size.
What we envision is three racks of 74 cubic meters, and I don't know what size exactly it takes.
Okay, and okay, another question I will take from, what is the efficiency of the overall process? I don't know whether someone can reply. So total energy spent in producing, compressing and transportation of H2 compared to that is produced by gas turbine for electrification and heating.
Maybe we can give you some rough estimates. for two cases, since we have been talking about this 30% case and the 100% case. For the 30% case, it is on the order of the cogen efficiency of 80%, and for the 100% case, it will go down somewhere on the order of 45%.
Okay.
Basically, the hydrogen content, when I say this percentage, volume percent hydrogen.
Okay, and then I see that, okay, we are already over the time. Just maybe the last question we can take, and this I think would be more addressed to Siemens. With that size 125 megawatt electrolyzer, you will produce about 20 kilogram per hour of hydrogen. How much hydrogen will the gas turbine consume if running 100% hydrogen at base load?
This is roughly, you would use 1 ton of hydrogen per hour.
Okay. Okay, I see there are some other questions, but unfortunately we are running out of time. So I will take note of these questions. But at the same time, I would like now to thank you, all the speakers and that joined this session, this webinar. I also would like to remind you that about the next episode, so the fourth episode of the flexible power generation series. The registration are open, so soon you will receive an email, and I'm not sure whether Elisa, you could share the link in the chat box. And yes, also here they remind me that all the presentation will be available on the ETN's website. So thanks a lot also for all the participants to join us, and yeah, I wish you a nice day. Thanks. Thank you.
Thank you.
Bye-bye.